Good afternoon, dear students. Today we will continue talking about the methodologies by which we can reduce the reactivity of silanol group, and in this case, we can prohibit the undesirable effects of free silanols. We mentioned so far a group of strategies, starting the talk with the ion pairing, and we discuss this topic thoroughly. The second methodology, we can add a competitive base to the mobile phase, and in this case, silanols will be busy with competitive base instead of our analyte. And also, we talked about encapping of reverse phase columns, that the remnant silanols can be capped with small entities such as TMS. And also we talked about the purification of silica to get type B silica, and type B silica is less reactive and more suitable for basic compounds. Continuing the talk with this subject, we will mention other strategies such as ion suppression. Now, ion suppression, that we can suppress ionization of analytes, and also we can suppress ionization of silanols. Before talking deeply about ion suppression, I have to mention that reverse phase column cannot tolerate strongly acidic media nor strongly basic media. And the reason that in the bond is ether bond, okay? Although we have it with silicon, and silicon from the same group of the carbon. So ether can be broken in highly acidic medium, strongly acidic medium. So if we use the mobile phase with pH below 2, in this case, we will break down hydrocarbons via the protonation of oxygen atom here of the ether. So using strongly acidic media, generally speaking, can break down hydrocarbons of reverse phase columns. So it's a taboo to use pH below 2. Meanwhile, we cannot use pH above 8. Now, pH of mobile phase above 8 will dissolve silica. The reason that pH above 8 will be abundant of OH minus. Now, one of the organic characters of silicon, that it is highly fluorophilic and highly oxophilic. What do you mean of this? That silicon is oxygen lover and also fluoro or fluorine lover. It reacts strongly with fluor and strongly with oxygen. That's why we have silicon with oxygen, silicon dioxide. And the only acid which can dissolve the glass, which is silicon dioxide, is HF, because silicon is fluorophilic. The same thing that when we have silicon in a polymer of silica, okay, if the pH of the mobile phase above 8, we will have abundant quantity of OH minus. Now, oxygen in OH minus here will react with silicon in the polymeric form. Now, silicon will be broken down to monomers. So we will dissolve the polymer to monomers due to what? The abundance of oxygen in basic medium. So the perfect pH range of reverse phase columns, particularly silica-based reverse phase column, which are the most dominant columns, the pH of stability between 2 and 8. So we cannot use a mobile phase beyond this range. We have to stick with pH between 2 to 8. Okay? Now, ion suppression, that we can reduce pH of the mobile phase in order to suppress ionization of silanols. Okay? Now, silanols has a pKa of around 4. This is the average pKa of silanols. Okay? We have more or less wide range of pKa's for silanols, but the average is around 4. So we will stick with this number. Now, you know that if we have acid with pKa 4, then at pH 3, we have pH 3, then silanols will be suppressed with 90% of the groups. So 90% of silanols at pH 3 can be suppressed. If we use pH just 1 unit above 4, 5, 90% of silanols will be ionized. So here we have at pH 5 pKa silanols, 90% of them ionized, and at pH 3, 90% will be unionized. Or in other words, the silanols will be suppressed. I mean, in terms of ionization. Thus, using mobile phase with pH 3 or below, but not lower than 2, guarantee that silanols are less reactive, they are in unionized form, and in this case you will prohibit the probability of reacting between silanol as an anion with your analyte as a cation. Okay? So in this case, instead of having salt bridge between analyte and silanols, we suppress the ionization of silanols, and just hydrogen bonding might be formed between analyte and silanols. But in the worst case scenario, that the strong ionic interaction is ignored, and we just might have hydrogen bonding. So hydrogen bonding is not as equal as or as strong as ionic interaction. We will end up in this case with sharp peaks by using low pH. So it's better to stick with pH around 3 for the mobile phase, particularly for basic compound, in order to gain sharp peaks. Okay. On the other hand, if the mobile phase pH above 6, okay, for example, neutral pH, in this case, the majority of silanols, due to their pKa's, will be ionized. So silanol will prefer to make salt bridge with analytes, and this will induce some sort of tailing, as we discussed last time, that tailing will end up with bad resolution of peaks of analytes. Due to this fact, the majority of methods in United States pharmacopoeia have the pH of 3 for the mobile phase, or around 3. Okay. Now, you may say that if we increase pH, we will prohibit ionization of analytes. Unluckily, generally speaking, that basic compound, particularly nitrogen containing compound, have pKa from 9 to 10, okay, such as primary, secondary, or tertiary amines. Now, in order to get them in unionized form, I have to increase pH above 10, for example, 11, to make sure that 90% of these groups are in unionized form. You may conclude that the pH of stability for silica prohibit us to make such modification. We have to stick with the pH between 2 to 8. I cannot raise the pH of the mobile phase above 8 in order to make the analyze unionized. So the only option to me is to suppress ionization of silanols by using acidic pH medium. So this is the idea of ion suppression, by which we can reduce the tailing effect of reverse phase columns, particularly with basic compounds. Now, you may say that we have many options so far. Shall we use just a unique option, or we can mix more than one option? The answer, in practice, we mix more than one option. So we use ion suppression sometimes with ion pairing agent. Now, the good thing that in ion pairing agent, sulfonate cannot be suppressed by pH 3. The reason that pKa of sulfonate around 1.5 or 1.2, something like this. So these acidic groups need pH below 1 in order to be in unionized form. Okay, so we can use ion pair. We can guarantee in this case at pH 3, we can guarantee that sulfonate is still working as detergent, as ion pairing agent. And the same thing that the basic compound, of course, will be in cationic form, in ionized form, in such pH. So we can mix more than a strategy. And also we can use in cap column with these conditions. Some new technologies mentioned in the literature, and we have honestly some commercially available columns relying on these technologies. I will mention one of them is polymeric derivatization. Polymeric derivatization. What do you mean of polymeric derivatization of silica? That we know that derivatization of silica, that we can add hydrocarbon, as we mentioned, to interact with silanols. Okay. Now, polymeric derivatization, instead of having one entity of hydrocarbon for each silanol, we might have a group of hydrocarbons for even one silanol. Okay. So we have hydrocarbons like this, and these hydrocarbons are attached to each other. Okay. And they have silicon head with a chlor. Now, once we have silica with silanol group, in this case, we will have what? Covalent bond formation with silica surface. And covalent bond formation, if we have other silanols, they might not be derivatized by hydrocarbons, but they are covered by the polymeric form of hydrocarbons. Okay? Now, this continuous chain of hydrocarbons will cover the underivatized silanols. Although they are free silanols, but although they are free silanols, they are not significantly affect the performance of separation due to the covering of silanols with hydrocarbon chain, the polymeric form of hydrocarbons. So not necessary to have one derivatization of hydrocarbons with each silanols. Okay, the other silanols, and particularly inaccessible silanols, they will be covered by the polymeric chain of hydrocarbons. So the silica particles, will be covered by what? By chain of hydrocarbons. Even though we have some free silanols, but they are not accessible for the mobile phase. They are covered by the chain of hydrocarbons. Okay. Now this is a good strategy, and this ends up with sharp peaks, but they are usually more expensive than the basic form of the reverse phase columns. Okay. Also, we have another new technology, which is uh, polar embedded group technology. Polar embedded group technology. So if we have silica, we have derivatization of silica. Okay, and you know that we might have free silanols. The scientists thought that we can reduce the reactivity of free silanols by exploiting the reduction of reactivity of vicinal and geminal silanol. If you remember that geminal and vicinal silanols, they have low reactivity due to the mutual hydrogen bond interaction, which end up with low effect of silanols on the performance of separation. But how can we deal with the free silanols? We don't have adjacent silanols. We can add to the hydrocarbon amide or urea groups. For example, if you add urea is a form of amide, of course. Now, if you have, if in addition of hydrocarbons, so urea or just amide like this, okay, urea or amide will be polar, a group part of hydrocarbon. That's why we call it polar embedded group technology. That this kind of, let's make carbonyl here, this kind of group will enhance hydrogen bond formation between hydrogen of silanols and oxygen of carbonyl. The same thing for oxygen of silanol with hydrogen of amide or urea. In other words, we have simply chance for hydrogen bond accepting and hydrogen bond donation between silanol and amide or silanol and urea. Okay, we have, so just to see it's very good. I will make. So if you see here the silanols, we have oxygen with hydrogen of amide. We have hydrogen bond formation, and hydrogen of silanol with oxygen of carbonyl of amide. or urea, the same thing. So we, in this case, obliged silanol to form hydrogen bond with adjacent polar group, which is part of derivatizing reagent. Now, silanol, nevertheless, is free. It cannot deteriorate the separation of analytes due to the mutual interaction between it and the polar group, which is part of the derivatizing reagent. That's why we call polar part, which is the amide part here, polar embedded group, because it is embedded between silica and hydrocarbon. Of course, this kind of columns is more expensive than the classical columns, and it can significantly reduce the tailing of basic analytes. So in this case, we cover the majority of the strategies by which we can solve the problem of tailing. If you just to recap these methods again, that we can use ion suppression to suppress the ionization of silanols and to, in this case, prohibit the interaction between ionized form of silanol with ionized form of analyte. The second strategy, we can use polymeric derivatization to cover underivatized silanols below the sheet of hydrocarbon chain. Also, we can use polar embedded group technology to keep silanols, I mean the free silanols, busy with amide or urea groups, which are embedded between hydrocarbon and silica surface. And also we can use competitive base to make silanols busy with intentionally added basic entities to the mobile phase to leave our analytes with its own. And also we mention end capping, which is using a small entity such as DMS to block the activity of silanols. And also we discuss ion pairing reagent, which can be added to the mobile phase in order to reduce the ionization of the analyte from one hand, and on the other hand to make a new complex which is more hydrophobic than the parent compound. This resulted in increasing the capacity factor, the retention factor of the analyte inside the column, and consequently the chance of separation will be enhanced drastically. This method, we said that it can form another mechanism when detergent such as SLS immersed among the molecules of hydrocarbons in the surface, and in this case hydrophobic will be dominated, and the anionic form of surfactant will allow cationic exchange to be occurred. Okay, and in this case we mentioned all aspects for the for dealing with the free silanols, and the next lecture we will talk about other factors by which the chromatographic separation might be deteriorated.